Bismillahirrahmanirrahim. I'm Amal Suhail and my roll number is 21TE04. Today I'll be implementing Lab 7 of Digital Signal Processing, which is about frequency analysis of digital sequences. The objective of this lab is to study digital sequences in terms of frequency spectrum, contribution of high frequencies in a sequence, and contribution of low frequencies in a sequence. Task 1 of the lab is consider the following sequence. Plot the signal in MATLAB or Octave if sampling frequency is 20k samples per second. Then redraw the sequence after removing frequencies above 5 kHz. Observe and discuss the effects of this removal of frequencies. Then redraw the sequence after removing frequencies above 7 kHz. Observe and discuss the effect of this removal of frequencies. So let us observe the MATLAB code. Firstly, the sequence is defined x is equals to 1, 2, minus 1, 1, minus 2, 0, 2, 3. Then the sampling frequency is set to 20 kilohertz. Then the time vector is calculated based on the length of sequence x and the sampling frequency fs. It represents the time in seconds corresponding to each sample in the signal. Then the original signal x is plotted against time in the first subplot. This subplot visualizes the original signal's amplitude variation over time. Then, a Butterworth low-pass filter is designed with a cutoff frequency of 5 kHz. The filter coefficients are computed using the Butter function. The filter function is then used to apply this filter to the original signal x, resulting in the plot. The filter signal is plotted in the second subplot and showing the signal after removing frequencies above 5 kHz. Then, similar to the previous step, another Butterworth low-pass filter is designed with a cutoff frequency of 7 kHz, which means that it will remove the frequencies above 7 kHz. The filter coefficients are computed and used to filter the original signal x, producing filtered signal 7 kHz. This filter signal is plotted in the third subplot, depicting the signal after removing frequencies above 7 kHz. Each subplot is labeled with axis labels, titles, and grid lines to enhance readability. Let us observe the output. Here we can see this is the original signal. The red plot depicts the frequencies after removal of the frequencies above 5 kHz, and green plot represents the removal of frequencies after 7 kHz. We can also observe the stem plot for it. Here we can see that it is a stem plot. So the task 2 of the lab is use the following audio sequence, calculate the DFT. Remove the upper half of frequencies, that is frequencies above fs by 4, and observe the changes by listening the audio. Remove the lower half of frequencies, that is frequencies below fs by 4, and observe the changes by listening the audio. Let us see the MATLAB code for it. This code reads an audio file named music.wav.aac using the audio read function. The audio data is stored in the variable y, and the sampling frequency is stored in the variable fs. Then, the sound function is used to play the original audio stored in y at the sampling frequency fs. This allows us to listen the audio. The discrete Fourier transform of the audio signal y is computed using the FFT function. The result is stored in the variable DFT. The DFT represents the frequency content of the signal. Here the upper half of the frequencies, that is above Nyquist frequency, which is the half the sampling frequency fs by 2, are removed. This effectively means retaining the frequencies up to Nyquist frequency divided by 2, that is fs by 4. The code computes a frequency vector f representing the frequency bins corresponding to the elements of the DFT. It ranges from 0 Hz to just below the Nyquist frequency. Then a new figure is created to plot the magnitude spectrum and the original audio signal. Now let us observe this code by running the output. In the first subplot, the magnitude spectrum of the original audio signal is plotted against frequency. This plot shows the magnitude of each frequency component present in the audio signal. In the second subplot, the original audio sequence Y is plotted against time, which is converted to frequency using the sampling frequency Fs. This plot represents the amplitude variation of the audio signal over time. The next part of the task 2 reads an audio file by using audio read function. It then calculates a discrete Fourier transform using fast Fourier transform built-in MATLAB function. It then sets to 0 the upper half of the frequency components in DFT, effectively removing the frequencies above 1/4 of the sampling frequency, that is Fs by 4. This process DFT is inverse transformed to obtain the filtered audio signal by using IFFT function. Then finally the filtered audio is played using the sound function. So let us run the code and observe the sound effects. Here we have observed that the upper half of the frequencies are removed. Now, for the next part, it then sets the lower half of the frequency components in DFT to 0. In this task, we are going to remove the lower half of the frequencies. The operation eliminates the elements in the first half of the DFT array up to Nyquist frequency. The resulting filtered audio signal is obtained by applying the inverse fast Fourier transform algorithm to the modified DFT. And then finally, the modified filtered sound is played using the sound function. By running the code, we'll observe the sound effects. Here we have observed that the lower half of the frequencies, that is up to Nyquist frequency, are removed. Thank you so much for watching. See you in the next video. Allah Hafiz.